Good morning. How's everyone doing? Good? Is anyone else humbled by that walk from the hotel to here? Anyone else? Anyone speed walk it because you have a presentation in 30 minutes? You can feel the burn, I promise. So I'm going to set expectations for this talk very early. I was supposed to have a working demo for you. In fact, I was supposed to have coordinates that you could go to try what I built. I do not have that. But I've got some interesting concepts and some ideas, and this will be finished. But I actually need your help because what I started this project, I was kind of questioning, is this worth my time? Is this a worthwhile endeavor? And so I want to kind of delegate to the conj community to see if this actually is worth pursuing. And as we go through the presentation, that's going to make more sense as I talk about some of my bullet points. But first, let's talk about me. So who am I? So that's me. Hi, I'm Steven Lombardi. Nice to meet you all. Hi. I'm Lambo on GitHub, and I've been a professional software engineer for almost 15 years, coming up on 15 years in like 2025-ish, something like that. And I discovered Clojure in 2018. And I've been using Clojure professionally since 2019, 2020-ish, something like that. I work at Centripetal Networks. We've got the team here. Hi, guys. So I'm a senior engineer at Centripetal Networks. We use Polylith at Centripetal Networks. So just a sidebar, if any of you are into Polylith and want to talk Polylith, grab me in the hallway because I love our infrastructure and our stack and how we develop it at Centripetal, but that's a conversation for another time. I'm an avid country swing dancer. Yes. I was going to attach photos, but I didn't want to get a text or a call from any of the ladies I dance with and say, "You put me in the presentation?" So didn't do that. And I'm an amateur ventriloquist since 4th grade. I gave it up because while I was a pretty decent ventriloquist, I'm not very funny. Lastly, I've been playing drums in church for almost 20 years. That's been something I've been doing for a long time. And actually, I'm really spoiled at my current church. And I know in conj we have a couple of music nerds here. So let me actually show you real quick. So we actually, at my church where I play drums, we actually use software called Playback on the left right here. And I can play to a click track, we play to a metronome, and we have backing tracks. But one cool thing we do is we actually put MIDI cues in Playback to control ProPresenter for all of the lyrics. So lyrics are fully automated using MIDI cues in Playback. So all that to say, that's just a small tidbit. If you want to talk music tech, see me in the hallway. All right, and then lastly, for the final icebreaker, I feel like every engineer that I talk to who's been around for a few years, they always tell me, "Oh, when I was your age, I developed on a so-and-so, insert old technology here. Punch cards, whatever the case may be." Well, here's my story. So there's a lot going on in this photo. This is me in middle school. That's what happens if I don't cut my hair. The game I'm playing, I'm pretty sure, is the original Planet Side. Is anyone familiar with that? Maybe. Oh yeah, we got. All right. Oh, I played that, and then I rage quit. And that computer you're seeing right there is a Compaq. Compaq, yeah. So yeah, that's just a little. Okay, that's enough pleasantries. So, what I'm here to talk to you about today. So a while ago, I read a blog that Stuart Holloway published about debugging at the REPL without any stack traces or without any logs or anything, just by the feedback of your REPL. And I finished that blog and I thought, I wonder if there's a way to automate this so I don't have to manually type all of that into my REPL. So can I automate this process somehow? What would an opinionated ideal tool for tracing look like? And what other work has been done in this space? And so I started looking at the tracing tools and kind of coming up with my own criteria for what a good tracing mechanism might look like. And this is what I arrived at. This is very opinionated. Feel free to either agree or disagree. But the one thing I wanted is I wanted the tool to be lightweight. So what does that mean? That means no need for heavy dependencies or swapping out the Clojure jar entirely. And my thought process along these lines is, hey, it would be really cool if one day I can use this in production. Like, if something doesn't evaluate the way I expect, or if something doesn't compute to what I want, and it's a function and it's purely functional, who's to say you can't rerun it in production and store the traces for later analysis? Stateless. So no mutating or instrumenting functions. I don't want to keep track of what function I've redefed and what function has bytecode has been changed, and I don't want any workspace state. So when you're tracing, I don't want you sending like all of the traces to some workspace that you then have to clear. I want a return value. REPL driven. The REPL experience is priority and should be enhanced by the tool. So I want something that's usable at the REPL and doesn't require extra stuff to use. But if you wanted to, you could use tools like Portal or Morse or something else to augment what how you view your data. Zero touch, so no need to modify code. So you don't no print line debugging, no wrapping code and then unwrapping it. It just can trace it as is. And then data first. This is the big one. And as you'll see as we go through the talk, a lot of libraries are coupled to standard out. And I didn't want that. I wanted data. So, the trace report, the code should be executed as data, fully decoupled from standard out. So let's look at, let's spend some time talking about the ecosystem. Tools.trace. So tools.trace, this is a great go-to option. I love tools.trace. It's reliable, it gets the job done. If you want something quick, use it. It's great. It comes really close to the goal if every namespace on the class path, including dependencies, gets instrumented. Now, I haven't run any tests with all that instrumented. I don't know what happens when you do that, but I'm trying to avoid that. So I would say, yes, it's lightweight. It's not stateless, at least by my definition. Is it REPL driven? Depends on the editor. How good is your editor at supporting standard out? Depends. It is zero touch, but it's not data first. All right, let's look at another big one, the Flowstorm debugger. For Flowstorm debugger, so if you're learning Clojure and you're not sure how data is flowing through your system, this is a fantastic option. You get a lot of introspection power from Flowstorm debugger. So for exploratory purposes, I highly recommend it. But there's a couple of issues I have with it in my workflow in particular. So if you want to, they have two ways to set up Flowstorm. The Clojure Storm setup requires swapping out the Clojure jar, and it comes with a disclaimer for dev only. Vanilla Flowstorm, which is, let me caveat, is also dev only. Vanilla Flowstorm basically the setup for that requires instrumenting forms through reeval. So once again, you've got that stateful component. So I would say no, it's not lightweight for Clojure Storm. No, it's not stateless. Is it REPL driven? Well, it depends, right? It brings its own UI. So the UI that it brings, it has its own, I'm pretty sure it's a Swing UI. It brings its own UI, and you use that UI to explore your data. But it is kind of REPL driven because it lets you bring values back into the REPL for processing. So it's kind of on the fence there. It is zero touch, and technically it is data first because it does offer APIs that will return you data. All right, so now let's look at some others. Saeed. If you look back through conj talks, you will find that Bill gave a talk on Saeed, and this is actually a really popular option for folks who use Emacs because it's got great Emacs integration. But is it stateless? No, it requires instrumentation, and it does use a trace log, meaning as you're tracing, you're sending your traces to some state store somewhere, maybe at an atom, whatever the case may be, and you have to consequently clear that out in between your runs. And is it data first? I looked into this. As best I can tell, no, it's not data first, because it appears to output data to an Emacs buffer. Behind the scenes, it might be data, but I didn't see an immediately obvious way to access that data. There's another tool called Omnitrace. This is pretty cool because it actually lets you use flame graphs and other visuals, and it's purpose-built to be used with Portal because Portal supports Vega visualizations. And so this basically speaks the Vega language, so you can create really cool visualizations about your code. And it also offers an inner trace feature, which is what I'm trying to get at. But but it's not stateless. It does require instrumentation, and it does write traces to a workspace atom that has to be cleared. But it is data first. In fact, the inner trace report that Omnitrace uses is very similar to what I use for the report. It's just a map with a form and a result. This one's a cool one. GNL playback. This one's really cool. It has a lot of good ideas, but it's not zero touch, and it is data first, and it really stresses that. But one of the drawbacks is if you use it, it brings in Portal with it. So if you add it as a dependency, you're depending on Portal too, so you can't pull in the visualization tool you would like a la carte. And then there's others I looked at. I looked at Debugs, I looked at SpyScope, I looked at HashP, I looked at Snitch, and I looked at a couple of others, and this is kind of the pattern I found. The two areas where they kind of fall short, they're not zero touch. They all require modification to trace, and they're not data first, they're all coupled to standard out. And then just a disclaimer, all maintainers who see this, shoot me a message, I would love to be wrong. All right, so what do we do? So the tool that I visualized, and so right now when you're at your REPL, anyone can run a function at the REPL and get a result. So what I wanted to do is to create a library with an API to run any function, but instead it returns a trace report as data, and then you send that wherever you want to send it. And this data can be inspected at the REPL itself. So if you're a REPL fan and you don't like the visual editors, you've got all the benefits of the REPL. And if you like, then you can use that with anything else you want. And this is really cool because there was a lightning. For those of you who missed it, there was a lightning talk the other day about cursive and some of the new UI features that are coming in it. These UI features fit perfectly with the goal I'm trying to accomplish. You've got Portal, you've got Morse, and even the upcoming features in cursive. It lets you send data and annotate that data either using tagged literals, either using metadata, and then it impacts how that data is presented to you in the tool. So it offers quite a degree of customization. So, all right, so so it's in a little bit of a rough state, but I don't care, I open sourced it this morning. So if you wanna, it's in a rough state, but if you wanna take a look at it, that's the link. I made a tool called Papertrail. I went through 3 iterations, and all 3 iterations are still there. So forgive me, it's a little messy, but I'm going to go through like the latest iteration and show you what I've done. How does it work? So every invocation, instead of calling the function normally, we grab the function source code, and we interpret the code, and we lazily build the report. And all that boils down to is all I'm doing is I'm applying functions. That's all I'm doing. I'm not calling eval, I'm just applying functions and expanding macros. I'm doing a lot of what the Clojure compiler does, and I'll show you that in a subsequent slide. So yeah, interpretation in the latest version is divided into 2 phases, command generation and command execution using a call stack. So basically what I made, I kind of call this like an event-sourced interpreter because I have a schema of commands that can tell the interpreter what to do with itself. And then I have some functions that map Clojure's primitives to a sequence of those commands. And this will become more evident when I show you source code. Allow the user to control the level of nesting. By default, the trace will not recursively trace into other functions, but it can. This is coming soon. This gets really interesting when you go to implement try-catch finally. Because in try-catch finally, you have to know the context of how many functions you need to go up to find where you're catching or if you're just throwing entirely. And you basically get 80% of the way there by macro expanding everything, applying functions, and implementing special forms. So let's take a quick refresher. The Clojure evaluation refresher. This is pretty crude, but it kind of gets the picture across. So, and I really want to drive this home because when I get towards the end and I start talking about some of the challenges with this project, this model is going to help a little bit because the reader can be a little bit of a pain to work with because if you have an anonymous function, that gets resolved in the reader, not in the later stages. I'll come back to that. I'm rambling now. So you basically have a REPL user
or a source file. It goes to the reader. The reader turns it into data structures. It repeatedly gets macro expanded as needed, and then it goes to the compiler, and then you get bytecode. That's roughly how it works. This is what I do. Anything in red is something that I'm calling, not modifying. Anything in blue is novel functionality. So I'm calling my code calls the reader. So I read why? Because I'm reading source code from the class path directly, so I have to call the reader. And there's a flag that makes it safe to call the reader, so you don't automatically evaluate code when you call it. So I set that flag as well. I call macro expand. More on that later. There is an interesting problem when it comes to macros, and I will go into that in a bit. And then what I do is when I have the in-memory data structures, I have one function for every Clojure primitive that will map it to commands, and then I have a very lightweight, sort of like something that resembles an automata. It's basically just a call stack that just keeps track of arguments and the application of functions. So it's basically got a function, push arguments onto the stack, pop the args, apply a function, push the result back on the stack. That's all I'm doing. Like rudimentary computer science stuff. And then what you end up getting is paper trail bytecode, because yes, we compiled my code to bytecode and we compiled your code to bytecode, but your code is being, what's a good way of saying it? Your code is being interpolated, is how I would say it, by my code. I'm going through your source, looking up your function in the namespace, grabbing that function, and then calling apply. And I'm doing that for every function that I find. Okay, what about custom macros? This is the million-dollar question. What do we do about custom macros? Because, like, frankly, you can't trace the macro arguments prior to invoking the macro, because you'll lose all the context present in the macro's rearranging of its inputs. So, and also, it's impossible to code for the semantics of every macro and every library you might use. So here's a fun takeaway. I don't know if you guys knew this. Macro expand preserves metadata on forms. So if you set metadata on a form and you call macro expand and you search that form, the metadata is still there. So I can keep track of what your arguments are. So I annotate the macro argument forms with a metadata flag. I expand the macro. And then I interpret the expanded macro, but I don't submit the results to the report unless you're inside one of the annotated arg forms. Now, you don't have a guarantee on what the order of the report will look like, because the macro can rewrite it however it wants, but you'll get a reasonable approximation of what's happening behind the scenes. And then when the macro is done, report the final value from the macro to the report. Okay, and now for some code.
So we've actually, I tried to preempt, the problem. We've had the font size has never been sufficient, but is this sufficient? Okay, good. So let's start. So there's a couple, I want to actually show you the journey we went on. What I'm going to do is, I'm going to show you the journey we went on because I think it's interesting and we've got time. Where is it? Let's see, where are you at? Here we go. Okay. So my first attempt at this, I created a recursive descent interpreter, which basically just uses plain recursion, and the grammar is expressed by the recursive calls in the functions. So what am I doing here? So handle defn delegates to handle form when it doesn't know what's coming, and it recurs all over the criteria of the defn, and handle list. What does it do? It will recursively handle a list if there's a list inside of it. Everything's recursive. And this was just a quick and dirty prototype to say, hey, is there any value here? But it doesn't work because, Stack Overflow, right? So it's like it's not viable. But so then we went on to the second version. Actually, worth noting here. Hang on, worth noting. Yeah, worth noting here before we move on. So I actually implemented support for destructuring in the first version. I just haven't brought it over to the third version. So, and it still uses plain vanilla recursion. And what's really cool when you're writing support for destructuring, and when you're writing support for just bindings in general, all you really need is just a map of symbols to their values, and that represents the context at any particular position as you're interpreting the code. And that'll become more evident as I continue to show. So now let's go to the next iteration. So the next iteration revolves around you basically getting the form and creating a child seek, which basically is a form of tree seek, basically using tree seek on the list. And this was interesting, but it had some problems with it. What I ended up doing is I ended up having a forward pass over the data and a reverse pass over the data in order to do what I wanted to do, and it was just gross to maintain. Like, I was doing coding gymnastics trying to account for, okay, in the tree seek, how many redundant forms do I have? Well, how many do I need to skip? Because the tree seek will give you the parent, but then it will give you all the children inside of it. But in that child, it gives you the parent and then all the children inside of it. So there's a little bit of redundancy you have to account for. And after working with this for about a month, I was like, no, I don't like this. So now let's go to where I actually arrived. This I'm actually happy with. So let's start with, where is it here? All right, here we go. I want to give you the data structure. Where's the data structure? Yeah, here we go, data structure, okay. Some people read code logic first, data second. I tend to read code data first, logic second. It's just how I tend to do it, so that I can verify that everything's operating on what should be there. So here's the data structure. So the top level structure is, we have a function IDX, which is just an index of, hey, in the function stack, which context are we currently working with, and that's this list right here. And what we're doing there is, every time you recursively trace into another function, you're gonna need another context. That's why I have a collection here. You need to start from scratch and new up another context and basically run the new function from there. And then I need a flag to know if I'm in a throwing state or not as I'm interpreting the code. The function context looks like this. So it has the list of commands. So all the commands I'm working, it has the command history. So every time I take off a command, I put it in history. It has the call stack, which is just where I'm pushing arguments. And then it's got two maps that represent scope. So what names are in scope for me? There's source scope and there's impulse scope. I have two of them because macros like to add their own scope to the code that's being executed. But when you browse the source, you don't see that. So it doesn't make sense to, in the report, show the scope that's both impulse scope and source scope. Does that make sense? And then I've got state. This is just where if the interpreter needs to store some state, it'll just throw values on there for later use. And then the commands, some of the commands, they look like this. So there's a command that basically just advances to the next command. There's a command that invokes a function. There's a command that invokes a function. There's a command that knows how to process a scalar, just a simple value that we don't need to do anything else with. We know how to, at any point we can capture state from the call stack. We can bind a name. So, hey, this a let binding was just put here. I'm gonna bind its name. Or hey, loop and recur just did some bindings. I need to bind a name. I can call this multiple times for every instance. And then I can unbind a name. Then I need branching capabilities so I can execute code when something's true. So basically what this does is for the next X commands, it'll execute them when a condition is truthy. And then the opposite, it'll skip it'll skip the next X commands when it's truthy. And then we can replay the commands for loop and recur, and for other looping structures, we can replay the commands. So yeah, this kind of resembles a form of bytecode, right? It's like an intermediate thing that I'm using to interpret the code. Now let me show you where this implementation shines, is in how we define the primitives. So here we go. So every primitive function is just a concatenation of commands that can be executed by that runtime I just showed you. So handle invoke, so for invoking any function, well, and also I have to mention this. In the attribute map that I'm passing around to all of these handlers, there is a function called form to commands. And that is if you have some form that you encounter when writing these handlers, but you're not sure what it is, just call form to commands, and it will safely recurse using lazy seek and generate the proper commands for you. So what does that look like in practice? So the commands for a function invocation take the args, form to commands, pass the attributes, and basically mapcat for all of the args, just call form to commands. That will give you commands for those forms. Then throw them, begin form. What are we doing? The operation is the first in the form. Are we in a macro impl? And what type of operation are we doing? In this case, it's just a function. Then concatenate the commands, and then after the commands have been concatenated, invoke the function that we are trying to invoke, because now its arguments are going to be on the call stack. And then end the form. Now, if you look at this data structure, I took inspiration from JSON parsing. Because there's two, when in the JSON parsing community, there's two general ways, actually just in parsing in general. You can parse something DOM style, where everything goes into memory at once. You can also parse it, I think it's called stacks style, where it's event-based. So you don't need to keep the entire document in memory, you just get events as the parser encounters things in the document. So that's what this kind of mirrors, is the stack style. There's an event here, begin form, and then there's an end form event. So what you get is this sequential sequence of events, but you don't lose the nested structure of the original S expression. Here's an interesting one, handling if. So we know that in the, so if we drop the first two forms from an if we drop the if and if we drop the condition, and then we get the first thing, we know that that's going to be the condition in the positive case. And if we do it, but we get the second thing, we know that's going to be the condition in the negative case. So we generate commands for whatever those S expressions are, and then we just concatenate them in the proper position. Does that kind of make sense there? Okay. Here's the macro handling. So what we do is we macro expand the form, but before we do, we modify that form with the metadata. We modify the form with the metadata, and then we macro expand and we set the flag. And then what we've got to unset the flag is we've got middleware. We've got middleware here. Every operation is wrapped with this middleware. If we find that metadata, we toggle the flag back to false. And that's how we interpolate whether we're in a macros implementation or are we in the arguments and in the source code as you would read it naturally. So loop and recur are kind of interesting. In order to do loop and recur, you actually have to What I did is I had a special event called a recur target. So I've got a recur target right here. Let me pull this up here. There we go. And what that does is the recur target is a place that when I'm moving through events, it's a place I can go back to. And so what happens is when you set up a loop, you have to handle the bindings, and you have to handle all the bind names, but you also have to set the recur target. And then when you handle recur, if you encounter the end of the recur and your condition, and it's time, and you still need to recur, you have to replay the commands back to the recur target that I set earlier in the commands. So this is basically all the primitives that are handled right now, right here. There we go. So we've got, these are all the ones that are handled. If you see a symbol in this map, it is the first argument to a real form. If you see a keyword, it is a more general category. So for instance, function invocation is a general category. There's a lot of different first elements that can come in that list. And then this is form to commands. This is how we do it. So it's a lazy seek. It's a lazy seek. What we've tried to do is we try to find the proper handler by first looking at the first element of a form. If we can't find it, then what we do is we have a special function to classify the form because we couldn't find that first item in the list that actually corresponds to how we should handle the form. So then we try and classify it, and then I think by default we just consider it a scalar right now, but that'll probably change in the future. But as we go through this, we basically build up a lazy sequence of basically calls to these handlers. Now, something that's interesting about this, so let's go here. Yeah, nope. Yeah, here we go. So something that's really interesting about this, so I'm building an interpreter, which means I'm building a drop-in replacement for eval. So what that means is that if I want to test this thing, if I want to make sure I'm doing things correctly, well, there's a really easy and elegant way to do that. All I need to do for my test cases is declare forms. And if they eval to the same thing in both my interpreter and Clojure's default eval, then we're good. So I don't usually reach for macros, but here's a macro. And it's just an extension of the testing macro. And what you do is you just expand. It takes a message, so some message or context that will print if something goes wrong, and it takes variadic arguments of forms. And what it does is it makes sure that when it's passed to my eval and when it's passed to Clojure's eval, that they're equal. And so this is the test suite. It's just forms. And I stole this idea from an enterprise engineering idea, and I think it actually is used in aviation quite a bit. Is that, in aviation you've got multiple systems that are measuring things, but they might be measuring the same thing, and then they weigh in for consensus. Did we measure this? Did we all measure the same thing? That's one thing that inspired me to do this. Another thing that inspired me to do this is when you need to replace a legacy system, but the API stays the same. Well, why don't you just test any input against the legacy system and make sure that the new system you're writing, everything comes out equal? So that's kind of what inspired me to do this. What I did is there was another problem though, because the way tests fail doesn't always tell you what the root problem is. So what I did is I annotated all of my collections of forms with metadata that optionally down the road, I could run these tests in a particular order. And the order would basically inform us, well, how do I say this? Some forms only work if other more simpler forms work. Does that make sense? Right? There's a hierarchy in a way. And I know a lot of people consider it an anti-pattern to order your tests, but there was actually a really cool article. Anyone play video games on Steam at all? Yeah? Anyone play Factorio? Yeah, we got some Factorio fans. If you read their dev blog, they've got some interesting stuff on their dev blog. And one of the things they wrote for Factorio is they wrote a hierarchical test runner. And so their tests run in a dependency order based upon how the assertions will fail, so that if there's tests that really don't make sense to run because the prerequisites aren't met to validate those assumptions, they don't run and it fails fast. So down the road, I've got these collections of forms that are minimal, but as I go further along, I've got these collections of forms that are special. I've got these, collections of forms that are special. I've got tests for side effects. I've got tests for loop and recur, and then as you keep going, now I've got tests for core functionality, which is now that I've validated these base assumptions, does more typical code examples, do they work? All right, and then let's go back to the presentation. All right. Okay, here's a big question. I wanted to answer this question because there's an interpreter already on the Clojure market, and it's a good one. Anyone familiar with Borkdude's Psi interpreter? Yeah. So why not use it? It would have to be heavily modified to extract the traces. I actually had a conversation with him on Clojurians. I wanted to know if this was reasonable, and it's just not a good fit for what I wanted. And it doesn't fully support all of Clojure. It supports a generous subset, but not technically all of it. And Psi's focus it's to create a Clojure sandbox that's basically safe for scripting based upon the application. So what you do is when you're working with Psi, what you're doing is you're basically defining what functions are allowed to run in your sandbox. Well, that's not what I'm trying to do. I want an interpreter that works in your primary environment, not in a sandboxed environment. So that's why I didn't opt for reusing Psi. It just wouldn't be practical to do this. Okay, let's talk about current challenges. Anything to do with the reader. Let me give you an example. When you call read on source code as text, and if you've got the shorthand for functions in there, you immediately get a function implementation. Well, I can't trace that. I need source code. I need the raw code in order to trace something. So when I've got a raw function, implementation, and you guys know when you're at your REPL, it has the hashtag function. You guys know what I'm talking about? It's an actual function. It's not the raw form that I need. So that makes it hard, and it makes it hard to unit test. Because it's not, when that reader behavior it's not super reproducible to go both ways through the reader and back. Because now I'm losing a bunch of stuff. Now I do support it, and I'm going to have to revisit when I support tracing functions passed as arguments. I'm going to have to revisit this problem. Here's another problem. Extracting source code that's defed up at the REPL and not loaded from the class path. I'm thinking that some REPL middleware might be required to fully support everything. Because when you're defing up stuff at the REPL itself, it doesn't live anywhere. So where do I go on the class path to pull your source code? Well, if I've got middleware and I can intercept that, then I can maybe index it somehow or store it somehow or do something with it. And then I gave some thought to what does it look like to inject the interpreter into multi-threaded scenarios, and I'm debating if that's even something that's supported at this point. Okay, current roadmap. So finish, try, catch, finally support. If it's in bold, it means this needs to get done before I have people start messing with it. It's not on Clojures right now, but feel free to go to the repo and poke around. Port over log building. Right now, I build the log in my second version, but the third version doesn't build an actual trace log, it just evals right now. I need to move that functionality over. Port over destructuring, again, I support destructuring in the first version, I need to port that over to the third version. Recursive tracing into other functions. Okay, so what I want to support is, hey, you give me a number for how deep you want to recursively trace, and then when I find a function that's not a Clojure core function, I will recursively trace into it. Tracing for functions passed as arguments, that happens a lot in Clojure, map, reduce, etc. A flag for viewing the full trace of a particular macro expansion. I thought this might be useful. Anyone ever have to debug a nasty macro before? So I want to give a flag where, what it does is it basically, you get a full trace of the macro's implementation. Now that's not source code as you see it or read it, but it's still useful nonetheless. Optimizations for fetching source code. I'm doing class path work. I don't want to have to remember what file your symbol lives in. I need to add caching for that somehow. And then Clojure script support. I want this to be practically usable at some point.